And I know that's like why we talk about verbs and nouns in math class, but it's really important to understand the different ways that you can be presented the same question. All right, so do we all know how we're going to apply the product rule for this example? We need to split 5 sine x cosine x up into 2 distinct functions. Frequent question, where should the 5 go? You can either pull the 5 off initially, you can lump the 5 in with the sine x, or if you want to get crazy, you can lump the 5 in with the cosine x. Any of those options works, right? But the obvious and clear thing is we got to get the sine x and the cosine x into f and g separately, because we don't have a rule that explains what to do for those as a product, short of using the product rule. So we good with that idea? So just for sake of convenience, rather than having this extra thing to keep up with, I'm just going to go ahead and lump 5 with sine of x. Call that my lowercase f. Call that my lowercase g. Does everybody have a good picture of what sine of x and cosine of x's derivatives are? Or do you need to go back and find that in the reading? Or do you want to put it on the board? I could put it on the board just as easily. The derivative of cosine x and the derivative of sine x, right? Those are the 2 things we need to know. Sine's derivative is cosine x. Cosine's derivative is negative sine of x. Of course, now my product rule is getting in the way. So just squeeze that out. So there's the things that there's the facts you have to know to figure that out, right? And of course, the product rule itself. So, who wants to step me through this? Anybody feeling confident? Make a box. Because again, there's 4 pieces of information we got to keep up with, don't we? We need to keep up with what original f was, what original g word was. We need to keep up with what f prime is and g prime is. So this is just organization, right? Box method is just organization, which also happens to have a pretty nice little geometric thing going on when you plug the things back in and use product rule. So what was that? 5 sine x. What's the derivative of sine? Cosine, right? Where's that 5 going to go? It's just going to get pulled off. We're going to do the derivative. We're going to put the 5 right back on. So it's 5 cosine x, right? What's g? G's cosine. What's its derivative?
It's negative sine. Yeah.
Negative sine x. We're ready to plug these things into this formula, aren't we? All right, so this guy's going to be f times g prime, so that's going to be 5 sine times negative sine x. So what's that going to be? That's going to be negative 5 sine squared x. Does that make sense? So that's the first 2 terms. Then what happens with g f prime? Cosine times 5 cosine. So what's that? That's going to be 5 cosine squared x. Now, in this case, it happens to be that it's a negative and a positive. So there's no kicking in the sine squared x plus cosine squared x equals 1. And there's no rule for what to do with cosine squared minus a sine squared. So there's no simplifying this into anything easier. If we take it to Desmos to graph, and again, remember, Desmos takes any function and can calculate the derivative using the ddx operator, or by just putting this with the apostrophe, the prime, into it. So again, maybe that does actually tame out into something that I'm not thinking of, but I'm pretty sure that because it's a negative sine squared, and again, the 5 could have been pulled off altogether, right? But since it's a subtraction of those 2 squares, I don't think there's a simplification. But we should double check. Maybe I'm getting a little rusty in old age, who knows, right? So f of x equals 5 sine x cosine x. And it doesn't like that for some reason. I probably need to add some parentheses. Yeah, I need some parentheses. All right, now I do f prime of x. That doesn't look like it changed at all, does it? That steeper blue pattern there, it came from that. Again, came from that original guy right there. But that clearly didn't simplify into a 1 or anything like that. That's clearly got a big old wild random changes of highs and lows. But that's because we've got 5, -5 cosine or sine squared x and negative and positive 5 cosine x. Worst case scenario, these things could potentially add up to a 10 or a -10, but because they're on alternating highs and lows, they actually never pull that off, do they? The sum, think about the sum of two things. If they were both at their high points together, it would just be 10, right? Since each one could cap out at 5. But in this case, they're capping out 5 in exactly opposite places. So one's at its high, and the other one's maybe at its 0. Then the other one's at its high, and the other one's maybe at its 0, because sine and cosine are just offset enough to do that. So that looks, I don't see any simplification in that, just this wild pattern. Okay? So you'll want to take a minute or two to look at the work set questions like 17, 18, 19 and see how, of course, how product rule comes into play for those. Or not product, closure. I said that wrong. Or should we look at one with quotient just to be sure?
Sure.
We can sling a quotient up there, right?
Yeah.
So all I have to do to make an quotient rule problem is just have two things being divided. Now, obviously, if I chose sine of x over cosine of x, that would just end up leading to the tangent, right? So let's do something a little more interesting. Let's do something like 5 sine x divided by 2 cosine x. Now again, obviously, what is another way I could reimagine that? I could say 5 halves. We just pull straight off of that, right? But let's pretend like we don't have that option, because otherwise this is just the tangent one. All right? So this is my high function, or my f function. This is my low function, or my g function. And of course, I erase that, so quotient rule, short and sweet. Blah, blah, blah equals high d low, so f g prime minus g f prime all over g squared. Okay. So, what? Go over here. Of course, 5 sine of x is actually still the same, so we don't have to change that one at all. 2 cosine of x, though, so I guess I could slip a 2 into that. And, of course, the negative sine of x times 2 just becomes -2 sine of x, right? So, you good with that? Be in our box again, a little box to organize. Then we just go filling in the parts. F g prime is still going to be this times that. So I get what, -10 sine squared x? Now, of course, it's instead of plus, it's minus gf prime, right? So that last time I said we had a positive and a negative, and there wasn't going to be anything. This time we have something totally different going to happen. 2 cosine x times 5 cosine x is 10 cosine squared x. But this is after a minus sign, so minus 10 cosine squared x. Now, the denominator is just g squared. So 2 cosine becomes 4 cosine squared, right? Let's go ahead and pull off a -10/4, right? The 10 can be distributed from the, pulled out of the top 2 terms. The 4 can be pulled out of the bottom term. So I can pull off -10/4, or I can pull off -5 halves, right? And I'm going to be left with sine squared x plus cosine squared x over cosine squared x. Now, this is special. Sine squared x plus cosine squared x is a relationship of how the unit circle works. Remember, what's sine? Sine is the y coordinate, right? What's cosine? The x coordinate. What's x squared plus y squared in a unit circle? That's like Pythagorean theorem, isn't it? X squared plus y squared. And this is c squared. So what's the diagonal of a circle of any triangle that sits inside of a unit circle where the radius is always 1? That's always 1. So x squared plus y squared, when we're doing in a unit circle, and the x and the y represent the cosine and the sine, automatically equals 1. 1. So like the negative 5 halves of 1 over cosine squared x. Well, what's 1 over cosine? The reciprocal of cosine is secant, right? Where does the negative go? Because we pulled off the 5 halves, right? But what's the derivative of tan? Negative secant squared, right? So my 5 halves getting pulled off in addition to that. Otherwise, this is negative 5 halves secant squared. Now I realize there's probably a couple of things that we could go back and look at that a little closer. But again, we pull up the PDF file with this example. We're basically mirroring. There's the trig functions, and of course there's those crazy guys. Then we get to the good guys. And I have one small issue, don't I? I don't know where my negative came from. Where did that negative come from? So 5 times negative 2, because cosine's derivative is negative sine, minus 2 times that. I'm a little concerned about where the negative came from, because otherwise it should have been 5 halves secant squared. Can anybody spot where I might have accidentally put a negative where I shouldn't have? Oh, I wrote my formula backwards. G's OP. Low D high minus high D low. This we're backwards. I used the bad formula because I erased it and then put it back up quickly instead of thoughtfully. So yeah, I gave you the wrong formula. It's low D high, so G F prime minus high D low. So it's not the same as that with just a minus sign. It's actually that. Now that would have been this, then this, which was the negative, subtracted, so it would have been added. So yeah, that's where I got it down. Yeah, so that negative. Sorry about that, guys. But shame on you for not calling me out on my mistake. I know. Don't just trust me because I am more experienced, but I'm also getting older, and my brain's not quite where it used to be. So catch me on my mistakes if you spot me doing something. If not, we get puzzling answers like that. But yeah, otherwise without the 5 and the 2, that is exactly the same as the without the 5 and the 2, that's exactly the same as their equation number 6 we got. Okay. Where they just did the derivative of tangent is the same as the derivative of sine or cosine. I just had some extra numbers in there, right? My numbers could have been pulled out at any given time. Again, the big leap of faith is make sure you recognize that cosine squared x plus sine squared x equals 1 is an identity, and one that you want to inject in there as quickly as possible because that takes a lot of confusion out of the situation. And of course, when you're left with 1 over cosine, or in this case, 1 over cosine squared, recognizing that's the reciprocal relationship with secant. Okay. But yeah, let's say the derivatives of the remaining trig functions are exercises 17, 18, and 19. If I attempted to put anything else up in there, we would either have to use some of these crazy, like if I tried to throw a secant in there, we would have to use some of those other things. If I tried to throw a cosine or sine in there, any differently, I would have just given away one of the questions. So there's really no excellent examples of quotient rule that don't get insanely crazy or match up to one of the 3 you're supposed to do. Now, somebody does point out this little side note, and if you are memorizing these, they do point out. The minuses, the ones that have a negative derivative, are each of the co-functions. So cosine, cosecant, cotangent. Those are the ones that have negatives. So it's not as random as just say some of them are positive, some of them are negative. The co-functions are the ones that have derivatives that are negative. Well, I will let you guys have a little bit of work time then, and here in about 20 minutes, I'm going to at the very least introduce the channel. Although we won't really dig deep into it until I guess it'll be Monday. I'm trying to think how taking Friday is a digital day. For you guys, digital day, I think I'm just going to give you all a simple assignment about learning the difference between or learning about the rivalry between Newton and Leibniz. Just a little bit of historical context for calculus. So if y'all have any questions, let me know. Otherwise, I'll give y'all 20 minutes just kind of look at what you got on your plate already before I go and add anything in. Anything that you want to I know this thing that's up off the table there. We're doing redboarding I really want to get somebody making something with motors and transistors and capacitors and stuff instead of just circuits and lights. I got one in there, but I think you would like it. I don't know if y'all know. Did y'all get Hayden?
Yeah.
Did you see?
I think, yeah.
I think, he's got some electrical background already, so he might end up doing something with these projects. I'm not going to force him, of course, but I think we make an awesome science project for, go down to Hobbytown and just buy a whole collection of those strange parts from the front case there and just see what happens. You have to learn how to solder properly. One thing still on my to-do list is learn how to solder.
Soldering is pretty simple.
But it's simple, yeah, in concept, it's super simple. Raise the temperature, turn it to liquid, let it cool, let it turn back into a solid. The skill, the artistry that's involved is what eludes me.
It's like welding. It's simple on the surface, but once you actually get it, it's so
Yeah, part of it is I do not have steady hands. Thank God I had no interest in being a doctor because I could not do anything with my hands. I'm lucky I can draw a stick figure and it might be all shaky sometimes. I know it's like if I have Parkinson's or I drink too much coffee, I'll never know.